Welcome to part two. We just covered t-tests, both independent samples and paired samples t-test. Next, we'll be moving on to analysis of variance, also called ANOVA, which is basically an extension of a t-test. So we use ANOVA when we're comparing more than two groups. So in this case, we're comparing the means of two or more groups, the independent variable on one dependent variable, in order to determine if the group means are significantly different from each other. So we need to have a categorical or a nominal predictor that has at least two groups, and as well as a dependent variable that is continuous or interval ratio. So this probably sounds very similar to a t-test, which we've covered before. So typically we use ANOVA to test for differences among at least three groups, since the two-group case can be covered by the t-test. So when there's only two means to compare, the t-test and the ANOVA f-test are actually equivalent to each other. And if you square the t, it'll actually give you an f ratio for an ANOVA test. So the two tests are very closely related. For example, in the previous example that we looked at with the t-test looking at the two different bottles of wine, we could run that exact same test using ANOVA and just take the square root of the f value and it would equal the t-test. So again, t-tests allow us to decide whether the observed difference in the means of two groups is big enough to be considered statistically significant. Again, we know that the numbers can look different. They're obviously unequal, but are they significantly different enough to not be due to just chance? So you might ask yourself, for example, on our t-test example, if we wanted to compare a $10 bottle of wine, a $90 bottle of wine, and maybe a $50 bottle of wine, kind of middle of the road, you might ask yourself, why wouldn't you just run a bunch of t-tests? Why wouldn't you compare $10 to 50, 50 to 90, and $10 to 90? So each time that we're running a statistical test, we have that built-in buffer zone of that chance that we might be wrong. So again, our type 1 error. And we said that that's represented by our alpha or our p-level of 0.05 or 5%. So each time we run a test, we've built in this probability that there's a 5% chance that we'll be wrong and we might make a type 1 error. So the more t-tests that we run, the greater the chances become of making a type 1 error. So we're just compounding those potential error rates. So ANOVA is nice because it allows us to test for differences among means all simultaneously without having to break it up into pairs and testing each of those individually. So we're doing this by finding the average difference between means of multiple independent groups using the squared value of the difference between the means, or the variance, and we'll get into that a little bit more. For this first part here, for chapter 10, we're going to look at one-way analysis of variance, which is going to map onto our independent samples t-test. When we get into the other types of ANOVA, we'll talk about which one corresponds to the paired samples, as well as how you can kind of combine the two. So when we're comparing more than two groups, when we're talking about ANOVA, we're really going to be talking about variance or variability quite a bit. And I like these little illustrations here as a nice example of how we can talk about different types of variability. So there are two types of variability. We can talk about between groups and within groups. So as an example, let's say we want to compare men and women and on something like height. So on average, men tend to be taller than women, which is between groups. You're either in one group or the other. However, you also have variability within those groups. So not all men are the same height as other men, and not all women are the same height as other women. You have variability inside or within those groups. So analysis of variance is going to take both of those types of variability into account. So we can no longer just subtract means like we did in our t-test. Instead, we're going to be calculating an F statistic, which is a ratio of the two measures of variance, the between and the within groups. So we have these graphics here. You can see A at the very top. You can see we have three curves overlaid on top of each other. And you can see these lines represent the group means. So you can see the means are fairly close to each other, and there's a high degree of overlap among those three distributions. So it would be really hard to find a significant difference in those three groups. For B, you can see that the means are spread out quite a bit more. Those vertical lines are farther apart from each other, but you still have a high degree of overlap within or underneath the curves. So our ultimate goal that we're striving for with ANOVA is letter C down here. We want our means to be spread apart, so we want a lot of variability between or across groups, but we want to minimize the amount of variability within or underneath those curves that we see there. So letter C, we have very distinct means with low variability within. So that's going to be our optimal ratio in ANOVA when we're calculating our F-test. We talked about variance before at the very beginning of the course when we talked about standard deviation. We said that variance was a step on the way to getting standard deviation, or you could also think of it as the standard deviation squared. And I gave the example of different distributions of class test scores. Remember, we had a couple different classrooms. They all had averages of 80%, but the difference in variance was quite different. So here we have a smaller subset of this. You can see we have a couple means here. We have 28, 30, and 32, which would give us an average of 30. And then we have 20, 30, and 40, which would also give us an average of 30. However, these sets are telling different stories because the one on the right has greater variability or greater variance. So this is what we're going to use when we're calculating our analysis of variance. And again, your book goes through some examples by hand. I want to walk through conceptually how you would do it, but again, these hand calculations would be even more tedious than the t-test ones. So we'll definitely run this using SPSS, but I want you to understand the different types of variance and how we use them. Your book walks you through an example of a one-way ANOVA starting on page 106. They talk about differences across grade levels in spelling. Again, I wanted to give you a different example than what's in the book because you can read what's in the book, obviously. So for this one, let's pretend that we have graduate students from a variety of grad programs. We have arts and sciences, education, business, and law. And let's say that we surveyed them and we asked them to rate how important financial factors were in their decision to attend graduate school. Because we know in this day and age it could get a little pricey. So we had them rate on a 5-point scale how important financial factors were. And you can see we have a bar graph here that breaks it down for each graduate program. You can see that for arts and science, they appear to have the highest bar. Education and business look roughly equal, and law has the shortest. So the question that we want to ask is, are these bars significantly different from one another, and how can we calculate that out? Our first step might be to calculate the overall mean of financial factors as a whole, regardless of graduate program that you're enrolled in. So here I've just drawn a line here. If you calculate the financial factor rating for every single person, regardless of what program they're in, we get an overall mean of 3.588. And we would call this the grand mean because it's the mean of everyone. It's the mean of the means. So regardless of what program you're in, this is the overall mean. So our next step, if we wanted to calculate analysis of variance by hand, is we would want to calculate the between groups and within groups variability, or as what we're going to refer to it as sums of squares. So this slide looks very scary, but we'll walk through it just at a conceptual level. If this is something that helps you understand it, that's great. If your eyes glaze over a little bit through this, that's okay too. But really make sure that you stick with us when we get to the SPSS part because that's what's going to help you do your homework. So we have three types of sums of squares. We have between groups, within groups, and then what's called total. And again, this is just getting at that idea of variability or how much scores deviate from the mean. So to calculate our between group sums of squares, we would want to calculate that grand mean from the sample mean of each college for each score, and we'll walk through an example. For our within group sum of squares, we'll calculate the sample mean from each score, and for the total sums of squares, we'll subtract the grand mean from each score. So I want to walk you through just a visual example on how you would do this, and then we'll take a look at it in SPSS. So this is our first step. I started kind of backwards. I started with the total sum of squares because that one makes the most sense conceptually to understand. All we're doing here is we're calculating the total sum of squares by subtracting the grand mean, that 3.588, from every single score. So you can see in that column we have x minus the grand mean, we have our deviation, we square the deviation and then sum it all up. And that gives us our sums of squares total. It gives us 8.122. So again, we just subtracted that overall grand mean from every single individual person, not taking into account what group they're a member of. The second one on here is calculating the within group sums of squares. So this one's a little bit different. In this case, we're taking each score and subtracting the mean of the sample or the group, not the grand mean, the group mean from every single person. And then we do the exact same process. We're going to sum it and then square it and then sum all of those squared deviations. So you can see for arts and sciences, we had a group mean of 4.0. I subtracted 4.0 from every single arts and science person and then squared that. Then I jumped down to education. They had a mean of 3.75. I subtracted that from each education person's score, square that, and so on with law and business. So subtracting the group means from the people in that group, taking those deviations, squaring them and summing them all up. So you can see at the bottom, our sum of squares within is 4.256. Next and last, we have the sum of squares for between groups. And this one's kind of the weirdest one, I think, to wrap your brain around. But in this case, we're subtracting the grand mean, so we're going back to that 3.588. We're subtracting the grand mean from the sample mean, or the group, but we're doing it for every single score. So because I have 5 people in arts and sciences, the group or sample mean for arts and sciences was 4.0. I'm going to subtract the grand mean from the group mean of 4.0, and I'm going to do that 5 times over. So you can see that column here in the middle hasn't changed. We've subtracted 3.588 from 4.0, and we've done it 5 times, or for every single case. Same thing for education. We subtract 3.588 from 3.75, and we did it 4 times because there's 4 people in that group. So you can see now we've done the exact same process. We subtract those deviations, we square them, and we sum them all up. And that gives us a sum of squares between of 3.866. So now we've calculated these 3 types of variability, or these 3 types of sums of squares. So what do we do with these now in order to calculate our ANOVA test? In Chapter 10 of your book, there's Table 10.1 and Table 10.2. They give you some individual formulas on how to calculate your F statistic, which is our ANOVA test. What I think is an easier way to accomplish this is to use what's called an ANOVA source table. So basically this is a way to help us organize the calculations and see how they flow and how they all relate to achieving that F ratio. So you can see here, column number 1, we have the source of variability, and we've broken that down by our between sums of squares, our within, and our total. So that's represented in the second column here. Our degrees of freedom, we're going to have a degrees of freedom between, within, and total. And then this fourth column is our mean sums of squares, so our mean square error. And what we're going to do is take our sum of squares between, divide it by the degrees of freedom, and that's going to give us our mean square between. Similarly, we'll take our sum of squares within, divided by our degrees of freedom within, to get our mean square within. There is no mean square total. That's not a thing that exists, so you don't have to worry about that. And then the final stage is to take our mean square between, divide by the mean square within, and that's going to equal column 5, or our F ratio. So we said before we're comparing variability between to variability within, but we have to take into account our degrees of freedom, which in this case is how many groups we have and how many people are in all of those groups. So let's keep going with our example, and we'll fill in some numbers in the source table here. So these should look familiar. Our second column, we have our between group sum of squares, our within, and our total. And spoiler alert, we could have taken a shortcut because the between and within should sum to add up to the total. So in reality, if you were calculating this by hand, you wouldn't need to calculate all three of those. You could just calculate two of the three and use arithmetic to solve for the others. Now, our degrees of freedom are a little bit more complicated in ANOVA because we have a couple different types here. So our degrees of freedom between is just going to be the number of groups in our study minus 1. So again, our degrees of freedom have been haunting us a bit with this n minus 1. In this case, we have 4 groups or 4 graduate programs total. So 4 minus 1 is 3. So we have 3 degrees of freedom for between. For our degrees of freedom within, we're actually taking the sum of the individual degrees of freedom for each group, which is based on the number of people. So if you recall, arts and sciences had 5 people, so we would do 5 minus 1. The other groups each had 4 people, so we would do 4 minus 1. So we would end up with 4 plus 3 plus 3 plus 3 to give us 13 degrees of freedom within. A shortcut, on the other hand, is knowing that our total degrees of freedom is the all-around total number of people in our study minus 1. So we have 17 people total, and that gives us 16 degrees of freedom total. So again, whichever of those is easiest, the degrees of freedom between and within will sum to the total. So you can see how when we're starting out and looking at our sums of squares between and within, we have quite a bit more variability in the within compared to the between. And we said at the very beginning, looking at those hypothetical pictures of distributions, that we want to have more variability between groups and we want to minimize variability within. And you can see how those numbers actually flip-flop once we take into account degrees of freedom. So once we divide by this column, you can see now our between groups variability is winning over, which is what gives us this F ratio of 3.94. So we took this 1.289 divided by the within, and we end up with 3.94. So our next question would be, how do we know if that's statistically significant? And just like our t-test, there's an appendix in the back of the book, and you can look up using degrees of freedom what the critical or cutoff F value would be. However, we're going to use SPSS and walk through how we can tell whether or not it's statistically significant. In case you're very interested, this is the formula out of your textbook from table 10.1. Again, I think it's a little bit easier to visualize using that ANOVA source table, but if this makes more sense to you, absolutely be sure to take a look at that in the text. We have some SPSS commands. We're going to be in the same menu that analyze, compare means that we used for the t-test, except now we're going to do one-way ANOVA, and then we're also going to get a couple different options. So we'll flip over to SPSS here. Here we have our data in SPSS. You can see we have 2 variables. We have graduate program, which is our independent variable, and it has 4 levels because there are 4 different groups. And then we have the financial factor rating, which was that 1 to 5 scale. So we can see for grad program, I've just given numeric labels to classify them. Makes it a little easier than typing in arts and sciences because SPSS can't read that. If we go to variable view, I want to give it more detailed values. I want to know which group is which. That will help us when we're interpreting. So 1 was labeled the arts and science people. So I'm just going to say 1 equals arts and science and click add. 2 was our education people. 3 was our law people. And 4 was business. So I just added all of those value labels, and then you can hit OK. I want to tell SPSS that graduate program is a nominal variable, and I want to tell them that financial factor is scale. So if we go back to our data view now, you can see we have grad program and financial factors, nothing changed. If you go under this view menu, this is kind of cool. If you click on value labels, it will actually plug in the labels that we just gave it. So in case you can't remember what's what, that's kind of a nice little shortcut. So we want to go ahead and run our analysis of variance. We want to know, are the mean differences across these grad programs significantly different? Is financial factor a bigger deal for arts and sciences versus education versus law versus business? So we're going to use the Analyze menu, compare means, and one-way ANOVA. And you can see this is kind of similar to the dialog box for the t-test. It's asking for our dependent variable and also our grouping variable or grouping factor. So I'm going to put our financial importance on the dependent, and I'm going to put graduate program as our grouping factor. Unlike the t-test, we don't need to define the groups. SPSS is smart enough for ANOVA to know how to do that. And we'll just go ahead and click OK. So you can see here we have the most bare bones output that you've ever seen in your life, and I'll talk about the reason why it looks this way and what we might want to change for next time. So it's telling us that it ran a one-way ANOVA. You can see here financial factor is up there as our variable of interest. We have our between group sum of squares, our within groups, our total. All of these numbers should look incredibly familiar. It's exactly like our source table. However, we've added this last column here of the significance. So just like the rest of our tests, we want the significance to be less than 0.05. In this case, it is. So we would be very excited about this finding and conclude that there are significant differences in grad program when we're talking about financial factors in making the decision whether or not to attend grad school. So what is wrong with this scenario here? We don't know which groups are different from each other. So this box, our F test, this is sometimes called the omnibus test, and all it's telling us is that we have significant group differences somewhere. It's not telling us where those differences are. So your book talks about, in order to get that, you have to calculate what's called a post hoc test. And the post hoc test is basically going to make all possible group comparisons and tell you where specifically the significant findings are. So in order to get SPSS to do that, I should have given it a couple of other commands. So let's go back to our Analyze menu, back to Compare Means, back to One-Way ANOVA, and you can see my variables are still in here, which is nice. I'm going to click on this button here that says Post Hoc. So it gives us a list of all kinds of different post hoc tests we can do. You can play around with this if you like. A lot of them actually turn out very similar, so it doesn't make a huge difference. Generally in your field there will be some kind of convention or common one that's used, but your book uses what's called a Tukey test. So I'm just going to check the Tukey box and hit continue. And then the other thing that would be really nice to know is I'd like to know what my group differences are so I could report which group is higher or lower and what mean score that they have. So if we go under options, once my box pulls up here, you can see we can request some additional statistics. I'm going to click on descriptives and then just hit continue. This very top button of contrast, we won't cover that. Your book does talk a little bit about it, so if you're interested, you can play around with that. So I asked for my Tukey post hoc, I asked for descriptive statistics under options, and I can go ahead and hit OK now. So now you can see we have a much more interesting output that's come out of that test. Here we have the group means, standard deviations, minimum, maximum. We have all kinds of great descriptives by group now, which is very useful. You can see our ANOVA table has not changed. It's just like before. We're still seeing a significant F ratio at the 0.033 level. If we scroll down though, now we have our post hoc test, and this is what we're interested in. So here we have our Tukey test, and what it's doing is it's making every single comparison you can possibly make. It's telling you what the mean difference is between the two scores and whether or not that mean difference is statistically significant. So you can see if we look on the far left column, we have arts and science versus education. We have a mean difference of 0.25, and if we follow that row over, we can see the significance is 0.913. Definitely not even close to being below 0.05. So we have a non-significant difference between arts and science and education. They're basically the same. The next one though, we have arts and science versus law, and you can see here we have a mean difference of 1.25 with a little star on it, and if we follow that over, we see that that's considered statistically significant. We can do the same thing, arts and science and business, not significant. And then you can see it goes down and it kind of does the mirror reflection, all these. So we had arts and science and education was not significant. So not surprising, education versus arts and science is also the same test and not significant. So you can kind of eyeball this column here and we see that really the only significant difference is between arts and science and law school. So that is what is driving the F test, that significant difference between those two. So the ANOVA table up here told us that we had significant differences somewhere in our groups, and the post hoc told us specifically that it was between the group of arts and science and the group of law. Now, if you're reporting this to a reader, you'd probably want to give those group means, and that's why we asked for the descriptives up here. So we could say that arts and science rated financial factor as a 4 out of 5 as far as importance in their decision to attend grad school. The law school people rated it a 2.75 out of 5. So clearly the lawyers aren't worried about paying off those student loans. They have a great deal of confidence. If we scroll down a little bit more, there's a last box of output, and honestly you can ignore this one. It's just kind of some extra output that it spits out that's not meaningful to us. So we had our ANOVA source table, and we had our 2-key post hoc, and we had our group descriptives. So now we're armed with everything that we could possibly want to have in order to report the results to our reader. And jumping back to our slides here, we have again our SPSS commands with kind of some notes so you can see when you run this for your homework how to do it. I also posted a couple of handouts on Angel that walk you through even additional examples, so not the ones from these slides. And it has some screenshots and some annotated output. So hopefully feel free to take a look at that. Save it on your desktop for when you're writing your dissertation and you're racking your brain trying to remember how to run a one-way ANOVA. So hopefully those are helpful, and hopefully the SPSS walkthrough helped on these. Next time we'll talk about repeated measures ANOVA, and we'll also cover factorial ANOVA. So we'll be building on this, so stay tuned for more.